Today's version of our inverse problem seminar. So we are very happy today to have Tatiana Bubba from University of Ferrara, which will be talking about deeply learned regularization for sparse data tomography. Thanks so much for giving a talk, Tatiana.
Thank you very much for giving me the opportunity to speak today, and for the invitation. Is really a pleasure to be here. So as the title slides say, I will try to talk a bit about some of the approaches we developed in the last couple of years related to some problems in sparse tomography using some techniques at the interface between regularization theory and deep learning. So first of all, in case there is someone in the audience who is not familiar with what tomographic imaging is about, we are interested in recovering the attenuation function related to the internal structure of an object. In real life, objects can be human beings, but also other testing objects, for if you have in mind, for example, your luggage at the airport, but also a frame in a museum, and many other materials of which you would like to know what's inside, but you don't want to destroy the object, okay? So for the sake of this talk, I will stick to two-dimensional imaging. So you can think of these of slices of image. And in particular, in this slide, you are seeing a slice of a walnut. What the forward problems of tomography is that we take measurements, and these measurements are, as we will see in a moment, the result of pervading the object with X-rays. And what the result is that we collect some data, which we call projection, and then later on arrange in a sinogram. And this is the second image you see on the slides. The inverse problem, in the forward problem, we know the physical quantity and we compute the measurements. In the inverse problem, which is what the game is about and also the topic of this seminar, we want to go back. So we imagine that we don't know what's the internal structure of the object. We might have some limited information, but let's think that we don't know too much. And then from the sinogram, we want to recover its attenuation map. So it's X-ray attenuation. And we can do this because the X-ray have different attenuation property depending on the density of the object. So when they go through the object, we get a decay, which is exponential. And on the other side of the shooting beams, we found a detector that is able to detect the incoming flux of photons. Okay, so it's much complicated than this. This is the simplified model that will suffice for the sake of this talk. So we are generally given some measurements. These are noisy, and we want to recover the physical quantity, as you see here. How this is done mathematically is that often mathematicians use, especially for the two-dimensional case, the radon transform. So if you want to deal with higher dimensional object, in particular 3D, you should consider the X-ray transform that integrates over upper planes. But because in 2D the X-ray transform amounts to the radon transform, we stick with this name so that we know what we are talking about. And how it works is that in the most simplified mathematical model, which is not the one that you would find in the most advanced devices, but is the very first one that was actually implemented in the 60s and 70s, is that we have an array of X-ray sources. These are in a parallel beam modality. And what it does is that we have X-ray going through the object, which is this gray blob. And on the other side, as I said, there is a device that is able to count the photons. And this is called the detector. And after we start from a fixed angle, and after the detector has measured the information, the X-ray source generally rotates all around the object, taking all the possible measurements. And at the end, we get this collection of projection, which is arranged in a sinogram, which is called like this because it looks like a superposition of many sinusoidal curves. What it is this about is that assuming we have a collection of measurement u at different angles omega and different offsets s, what we want to do is to recover u, which is the attenuation map related to our gray blob. And how to do this was known even before, many decades before the first device was implemented, and actually was a bit of a knowledge that was not really available to Cormack and Hounsfield, who developed the first CT machine. But what it was based about was on back projecting the integral, and the first workable algorithm filtered on top of this operation. That produced what in 2D is called filter back projection, and then it has many different variants when you upgrade these devices to different technologies in 2D, so with the fan beam, and especially when you go to 3D, where you can have cone beam or helicoidal beam, okay? So that's a research field in itself. What is great about filter back projection is that this is an analytical formula. Many devices still uses this. And when you have the possibility to scan an object with many angles, then the reconstruction you get is really great. On the other hand, X-ray is ionizing radiation. So if you are, for example, imaging parts of a human being, you might not want to take many X-rays. And if you do have to take this, for example, it's done in certain cancer screenings, then you want to use as little X-ray radiation as possible, because this can be harmful for human beings. So when we started to reduce the X-ray intensity, so the voltages, or we decide to take only fewer projection than we could, so we have what is called scarcely sampled angles, or it could be scarcely sampled also in the S variable, but we are not concerned with this today, then the filter back projection does not work as well as it does with full angular sampling. And on top of this, there is always some form of instability when you try to apply the algorithm, if your data are noisy, and some sort of noise is unavoidable in these circumstances. Okay. How do we cater this in the discrete setting? Is that we can, by kind of ignoring some of the physics behind this model, for example, scattering, we come down to having a linear model, which corresponds to a discretized, let's call it line integral. In general, it's the stripe integral. And in the end, we have a linear system depending on many variables. It's all the pixels that discretize our image. And what we have is some noisy data. This Y delta is the sinogram. R is the discretized version of our radon transform, X-ray transform. We want to recover U, and we assume that we have some noise. Assuming additive noise is maybe not the most accurate physics behind it, because it's photon noise. But on the other hand, this is done because after post-processing the data, often it's no longer a strictly Poisson distribution, and the counts of photons is so high that this is not a perfect assumption, but in many instances will do, okay? Once we have our discrete linear model, the resulting problem is still ill-posed. So in general, the ill-posedness of the full angle problem is very mild, but because later on we are concerned with cases where the angular variable is not fully sampled, the severity of the ill-posedness increases, right? So the less angle we have, the more complicated, the more ill-posed and ill-conditioned is the radon transform, okay? So FBP will not work well, and in practice there are a few options that one can investigate. For the sake of this talk, I'm interested in regularization. So what we do is that we recast this linear problem into the minimization of a functional. as bisfunctional as one term. The first one, this L2 norm, is what we call data mismatch or data minimization term. And basically, it measures the distance between the data we are given and how close, I mean, it basically contains the noise on the data, okay? And we want to minimize that. On the other end, because we don't want to overfit on the noise, we add some other term, which is called regularization. And this is usually an expression of our a priori beliefs in some properties that the solution might have. So this can be an L2 norm as well, and this provides generalized Tikhonov regularization, but it can also be, and this has been like widely investigated in the last couple of decades, I would say, an L1 norm of either the target itself or a transformation of it. And this is the case that depending on the field we are dealing with is called compressed sensing, sparse regularization, and L can be discrete differences, and then we are dealing with some form of total variation regularization, or can be wavelet of shearlets, so some other dictionary or orthonormal basis. Okay, so what happens when we have limited data as promised? So now we are looking at an image slice of a cucumber. And when we use FBP from full angle data, to convince you, I can see here we are using 180 angles, which is kind of a standard protocol for testing many algorithms. So we sample every 1 degree, and we get a pretty nice reconstruction. On the other hand, if we try to reconstruct our data, assuming 2 different protocols, probably the easiest to imagine is what I call sparse angle data. So here we don't have angles every 1 degree, but maybe we have it every, in this case, I think it's every 5 degrees, right? And what we see is that we cannot tell, I mean, we can see a circular shape, but probably if I hadn't told you it was a cucumber, you might have guessed other different vegetables, right? I mean, it could be a zucchini, right? And on the other end, limited angle data are obtained by limiting the angular variable in just a wedge, right? So we could assume, and now we formalize it, that instead of scanning all around the object, we only scan around a wedge of it. And so what you see is that because inside the wedge we have some form of dense scanning where the image seems to be informative, and outside of the wedge instead the information is not informative, as informative anymore. So what we do now is that we introduce the notation for this and try to formalize it a bit more from the mathematical perspective. So with our phi, I will indicate both sparse data operators, and to do so, we have to understand what it means. So in the limited angular case, it means that phi is the interval minus gamma gamma. And in the sparse angle case, rather than thinking of just the line going through the object, we imagine to have a certain direction, omega 1 and 2 being imaging plus minus eta around around this direction, and then we have some of this direction altogether, right? And in the discrete setting, how you achieve this is helpful, maybe in the more helpful in the second part of the talk, is that we are subsampling the matrix operator, the matrix corresponding to the radon operator with a mask where basically the elements are 0 or 1, and basically when we have a 1, we are saying we are selecting that direction. What we see from these images is that on the one hand, we have part of the edges that do not appear in the reconstruction. It's quite clear that in the limited angle case, we have kind of a missing part, while in the sparse case, we have many missing parts going around the object. On the other hand, we also see some edges that are unwanted, right? All these streak artifacts, so all these lines that are not part of the original target that we know of, because in this case we have a ground truth, are there, but they are artifacts with respect to the final reconstruction. The good news is that if we use microlocal analysis, we can understand a bit better why these some part of the edges we would like to have are not appearing, and on the other hand, some others are appearing and we don't want them. So to do this, some terminology. Probably most of you are familiar with what it is, a convolutional kernel operator and a pseudo-differential operator. So we are interested in convolutional operators because later on, when we connect to the deep learning part, we would like to draw some form of connection or link to convolutional neural networks. And so you can see on the slide what it means to have a convolutional kernel in general. Pseudo-differential operators instead are operators whose kernel is moved away from the main diagonal, okay? Now, from the theory of pseudo-differential operators applied to the case of the radon or in general of the X-ray transform, we know that the normal operator R star R associated with the radon transform is a convolutional one, where the kernel is the one associated with the expression on the slide, right? So it's x minus x, the inverse of x minus x prime. And this means that this is a pseudo-differential operator. For us, this is very important because it means it will preserve singularities. So in particular, this kind of gives intuition on why, when we reconstruct from the full angles, we get all our singularities, which it means edges for images, right? Instead, for the sparse data radon transform, this is no longer a pseudo-differential operator, but it belongs to a wider class, which is actually a generalization of the Fourier integral operators. And this categorization then explains the presence of the specific lines, because when we consider an FIO, then the singularities of the FIO can be propagated along specific lines. And so this is the reason why in the reconstruction we have singularities that are not meant to be there. These are propagated through the nature of the Fourier integral, of a generalization of the Fourier integral operator. So why do we care about this? Because if we introduce two more concepts, the singular support and the wavefront set, these have been studied extensively over the last 40 and so years in the case of tomographic imaging, and we are able to kind of fully characterize which edges we can expect to recover and those that are lost forever. Okay, forever. I mean, those that are lost are not present in the data, so we shouldn't be expecting to recover them. Okay, so the singular support consists of those points where U is not a smooth function, so it's like singularities associated with our function or distribution. And the wavefront set extends this notion by including not only the location, but also the direction of such a singularity. When it comes down to CT, and in particular here you see the case of limited angle tomography, we know that if we know the sinogram near a certain point, then we are able to detect the singularities that are tangent to the line passing through the point. Okay, so all those lines that are sampled in the radon transform we are able to recover, and these type of singularities are called visible. And those that are not in the measurements, so the singularities that are not to the sampled, tangent to the sampled lines, those are not generally available in the data, so we shouldn't expect to see those, okay? And so this is our starting point and gives insight in what in the images of the cucumber we saw at the beginning. Now, why do we care about this? The first approach I will present today builds on a work that I did while I was still a postdoc in Helsinki, together with Matti Lassas, Siamoli Siltanen, another colleague of mine, Luca Ratti, who continued in the project with me, and then Mathilde Gallinier and Marco Prato from the University of Modena and Reggio Emilia in Italy. And the idea there was to kind of think of a connecting point between what we know from the micro-local analysis perspective, what we know about regularization, and how these can help together to produce neural network strategy that can inform us about reducing artifacts, okay? And then we kind of extended this to take a bit more into account the micro-local perspective on this, and extend it also to the case of sparse angle tomography. So we need to take a few steps back. So let's consider again our inverse problem. The approach is general enough that it can tackle also other operators than those of sparse data tomography, but essentially you need a convolutional operator that has a Calderon-Zygmunt kernel, okay? But for the sake of this talk, just think about these two examples of sparse data tomography. And one approach, as I mentioned at the beginning, is to recast our inverse problems in the form of a minimization problem. We just consider a slight different formulation. So we consider as a special transformation the wavelet transform. And for example, in our test, we use like the easiest wavelet family you can think of. And then we take what it's in optimization is called the synthesis formulation. So we actually pose that our U is given by the, maybe let's do it this way, small w here is given by the wavelet transform applied to U. And then I recast the problem so that W here is my unknown, okay? And I can do this because usually, because the hard wavelet transform, and usually there are other families that one can use, but this one is orthogonal, so I can recast the problem, okay? In what is called a synthesis formulation. So the minimization problem applies to the wavelet coefficients, and once I find a suitable approximation, we'll see in a moment how I can recover the original target applying the adjoint wavelet transform, or it's like in the discrete counterpart, it's just its transpose, right? Its transpose, okay. Why do we care about this? Because the wavelet transform is able to capture the singular support of the image efficiently. So of course, there are more advanced transforms like shearlets and curvelets that are able to actually capture the wavefront set. So not just the jumps, but also the location of the jumps. But working with wavelets lessen a lot the burden both on theory and practice. And it was good enough for our scopes. The first thing that we can achieve by considering this problem is that there is a very famous algorithm that we can use to solve this minimization problem. It's called iterative soft thresholding, and what it does, for those of you who are very, very familiar with optimization, is that it takes a step on the smooth part of our functional, so on the data mismatch term, and then it takes the proximity operator associated with the L1 norm, okay? So our functional is convex, is non-smooth, but if we use the proximal gradient descent applied to this special case, we get exactly the iteration of ISTA. So what we do is that inside the parentheses, we have one step of ISTA. So we have, the gradient step with respect to the smooth part, and then the non-smoothness comes in the form of a soft thresholding operator, whose action is described here, is basically put into zero the certain components where let's say the length of this interval, because the soft thresholding operator applies pointwise, is applied pointwise, is defined by this parameter. And here lambda is the regularization parameter that balances the influence of the two terms, and capital L is the Lipschitz constant of the problem. Okay, so this algorithm has been used to solve also similar problems to this, where you have a smooth part and then a smooth part that is convex. And now this is the point where we start to draw a connection with the realm of machine learning, and in particular deep learning. So we can consider the generic expression of what is called a recurrent neural network. And here, how it works is that we assume to have some linear operator k here, and then we have a term which is, think of it as a vector, b is a bias, and then we apply a function rho, which is in general nonlinear. So these recurrent neural networks are made of a linear term to which we subsequently apply a nonlinear function, which is called generally an activation. Now, this, I think it is evident that reminds us of the iteration of ISTA, and generally we can think of this as unrolling the iteration of this network. How do we do this? Is that this term B here, so what acts as a bias vector contains the information about the data. Our K, so what contains the linear part, can be identified as the normal operator of the composition between the linear operator of our problem. Okay, for us A is just the limited data radon transform and the wavelet transform, and then the activation function is just the soft thresholding operator. If we set up the problem this way, we have two ways of doing learning. First of all, the idea is always to do this in a supervised fashion. So we set some learnable parameters theta, and in the original paper on learned ISTA by Gregor and LeCun, what they did is that they set as learnable parameters everything that was related with the elements of the K operator, so the K matrices, and also of the bias term. And then we defined a network that from the data should return us the solution. In our case, this is the transpose of the orthogonal wavelet transform applied to the solution, and the solution is computed such that if we go back, it's like you should think of this as unrolling the iteration of ISTA and truncating them after a few of them. So in the experiment I will show later, this amounts to 10, which is very different from what you do in practice in optimization, because you actually want to go to convergence, and for this type of algorithm you can prove that there is convergence of the iterations, but also that is very slow. So you actually take many of those steps from the traditional ISTA iteration. And then what the supervised learning paradigm does is that it finds the best theta, so the collection of the parameters that we want to find, minimizing what is called the empirical loss. So we have some training pairs, and in the supervised learning paradigm we have that the pairs are given by the sample data and some ground truth. So we suppose to know the data associated with the measurements that are provided, and we train until the loss is minimized. Okay, the empirical risk amounts to having some form of least squares. Okay. So starting from this initial idea, and this is not the only way you could do learning, you could also kind of learn what corresponds to the proximity operator. So replace a network, the soft thresholding operator, but this is a complete different approach, and I will not touch it, even though it's a very widely investigated avenue in this business. Okay. So what we did starting from this expression of the recurrent neural network, where we do some identification with the ISTA algorithm, was to actually add a correction term in the form of a convolutional neural network, so a network where the layers are convolutional, to the standard East iteration. So if you put beta equal to 0 for each n, then you retrieve the East iteration and you do at least as well as regular ISTA. But if beta is not 0, and in general this is among the learnable parameters for our framework, then this network here, which is convolutional, contains some parameters which are the entries of the filters, of the convolutional filters, where lays the potential to improve on the regular ISTA iteration. Let me try to convince you why this can work, and it's interesting also from a macrolocal angle, is that the structure of this network is not just any structure, but basically is built taking into account the convolutional nature of the limited data radon transform, okay? And even though I didn't report the result on the slides because it's quite technical, what we do is that because in lambda we are basically looking at the normal operator of A transpose A, but in the wavelet transform, when we combine the convolutional nature of both operators, we can write these networks as a convolution of upsampling, downsampling, and 2D convolution, like real convolution, not the type of convolution that is generally implemented in convolutional networks. And the filters are not just any convolutional filters, but take a special form, as we will see in the next slide, that comes from the geometry of the A transpose A operator, okay? And the reason why doing this can provide an additional improvement of the reconstruction is that we can actually interpret with lambda as the kernel of an operator, where a part of it is like fixed, and the rest, so this additional lambda is concentrated on the diagonal and at the center of it, so that I will show some images in a moment. What we are doing is mostly improving those parts where the Fourier FIO nature of our operator is transporting the singularities, okay? So let me try to say this also with some pictures. So first of all, what we can do is that the pointwise, I mean, from a theoretical point of view, from the pointwise application of the soft thresholding operator, we can recover edges and discontinuities that are invisible from the incomplete sinogram. To prove this, you actually need to derive a different, a continuous version of the network where you use semi-continuous wavelet transform. And at the end of the day, what you can prove is that the soft thresholding operator, which is applied component-wise to the subband of the wavelet transform, is able to add singularities whenever a wavelet coefficient crosses the plus minus gamma boundary, where gamma is basically the parameter setting how many let me go back here. So gamma is setting these intervals here, the length of these intervals, okay? And on the other end, so the second part, the kernel smoothing that comes from lambda, is that we can prevent strict artifacts from appearing, because basically the action of lambda, depending on the structure of the filters, is that of dampening the singularities and preventing those to kind of spread along the streaking lines as our as the microlocal interpretation suggests. The thing is that while the theory says that this can happen, we cannot foresee precisely where these additional singularities, which are potentially very good singularities for us, will come. So the idea is that the action of the soft thresholding operator can continue the edges we are interested in, but we cannot kind of foresee it from the theory. And the kernel smoothing instead has an action that spreads along the main lines and is very much concentrated at the center, okay? This is where we need it most, but also in this case, it might be that instead of preventing completely artifacts, is only able to soften them, okay? How do we do this from the implementation side? Is that we know, as I said before, from the design of the radon transform geometry, how the filters should appear. And in our initial paper, what we did was just that for simplicity, we just designed filters that were squared, and we allowed learnable parameters, everything inside a square, okay? So this made the implementation easy, but kind of didn't leverage as much as possible the microlocal insight. Instead, for the limited angle transform, we know that we should expect some bow type shape for the reconstruction. And this is what the bow type filters that we introduced in the latest work suggest. And our experiment showed, and so basically we are limiting the parameters to only be in these two halves of the bow tie. But what we learned during experiment was that actually we could even limit the learnable parameters to just be on the lines, and still you will see you get comparable result with the bow tie shape. And what you're doing here is that severely reducing the number of parameters you are learning, right? So in principle, you are making learning way easier, but what it means is that we are reducing the number of parameters. So in the square situation, if one size of the square is tau, you have tau squared the parameters. In the X filters, you have just 2 tau parameters. And then finally, for the sparse angle case, we basically kind of put to the stream this, it's like we are parameterizing the views of the that are sampled in the geometries, and it's like these filters are a bit more difficult to design in practice because, as you see, they tend to kind of cover too much the center. So in the limited angle results that I'll show you next, you will see that despite you have way less parameters, you still get very, very good result. With the other filters here, you actually need to take them to be twice the size of the largest wavelet subbands to really see some benefits. But this is also because it's like some numerical consideration on the way you implement these filters, and we use these masks on top of the regular filters. It kind of tends to over-represent, and it's like, yeah, I mean, I can give you more detail if you want. Maybe one thing that I should mention is that the theoretical part, even though I didn't show any formal result, it's kind of it's an adjustment of the results that Gitta Coutinho and Ozan Oktem and their group provided in a series of papers where they were able to actually derive a way stronger condition that did not apply just to the singular support, but to the wavefront set, and to what they call the digital wavefront set, and there they use shearlets. So that's a way stronger kind of tool from a theoretical point of view, and that's why they could deliver more information, not just about the jumps, but also about their location. Okay, so some result. What we will do now is pretty much compare to the different type of filters between them and see that what we get is that we are able to either prevent strict artifacts or kind of soften them, and that the image that we get appears as it does contain almost full information, even though it is not our goal with this kind of learning structure to kind of infer what is not in the data. Our achievement is just to be able to mostly preserve as much as possible the good singularities and remove those that are the bad ones. Okay, so the first set of measurements are on limited angle tomography. Now we only are imaging, so our gamma is pretty much plus minus 60 degrees. And what you see is that, well, you have the ground truth on the left. Then we are using in the column next to it the square filters. And you can see that pretty much even in the zoomed in regions, you are not able to see any streak artifacts, and the boundaries almost appear as being fully recovered, okay? And so this seems to be the beneficial action of the soft thresholding operator applied component-wise. And then you can see that if you reduce the number of parameters, either using the bow type shaped filters or using the X-type shaped filters, you pretty much get the same result. So even if you reduce the number of parameters, the reconstruction quality does not decrease at all. Okay, and in this case, as I said, we enrolled 10 layers and we trained for 15 epochs. This is the classic ellipse data set. If you want more details on the simulation regime, just let me know, and I'm happy to answer both. Now, if we reduce the visibility angles even more, so now we are basically measuring plus minus 30 degrees, we can draw similar consideration, right? So on the one end, there are some singularities. It's like, look at this very narrow ellipse here. With the square filters, it's not recovered, but instead with the, let's say, macrolacal inspired filters, we are able to see something. But be aware that basically this detail kind of falls almost out of the visible, it's like it's at the boundary of the visibility wedge of our system. Instead, on the other end, I think I've zoomed in a couple of, a couple of regions, but it's not a detail that is zoomed in, but here there is another detail, like another narrow ellipsis, that pretty much is felt to be recovered in all images, okay? So there are cases where it does not work. So that falls within the theory where I said it can allow for more good singularities to be present, but it might, we cannot be sure where this happens. And then for the sparse tomography, so we considered a very sparse angle. I have 12 angles here. So this is just 12 angles in all over the object. So it's very few directions. And regardless of this, you can see that the image appears to be pretty much complete. It's like there are no missing parts in the reconstruction. And if we even go down as to 6 angles, which is really, really low, you can see that, of course, you have some artifacts and some parts that are not really sharp. But considering that you have only 6 views around the object, this for us was pretty impressive, considering that the strategy we derived as anyway some form of backbone coming from regularization and optimization. Okay, so this was pretty much the first part of the talk. I know I'm close to finishing my time, but the second part is actually quite fast, and it's motivated from consideration about the backbone of unrolling. So in unrolling, what we do is that we start from the iteration of an iterative algorithm to minimize a functional, and then we truncate. So we only take a few layers which correspond to early stopping our iteration. And when we are done with the learning, there is actually no guarantee that what we recovered is somehow related to the initial minimization or optimization problem related to the original problem. So even if we get good reconstruction, we cannot really, when we talk about convergence, we need to agree on what we hope to recover in terms of convergence, right? So one way that this has been kind of not overcome, but kind of you can have another angle on doing something related to unrolling the steps of an iterative algorithms, but avoiding the problem on having to interrupt after a fixed number of iteration is the idea behind deep equilibrium, okay? So in deep equilibrium, what you do is that you effectively train an infinite number of layers without storing intermediate variables. So you can look at these from the standpoint of the fixed point iteration. And what you do is that you find a fixed point U bar of a suitable operator instead of unrolling a finite number of iterations. So effectively, you have an infinite amount of layers because you can run as many forward step as you want, but because we are not storing intermediate variables, the memory footprint of your algorithm doesn't change. And so we're able to do many of these iterations, okay? Not just something that corresponds ideally to 10 iterations. And here you see that this f theta here, which is the network, you can think of it also as a convolutional neural network, is where the implicit regularization relies, because it's able to inform some a priori properties on the fixed point. And in some way, if you are familiar with it, there is some connection to how denoisers work in plug and play approaches, okay? And here, so theta is again the vector of the learnable parameters. Alpha and gamma are some parameters that needs to be set by us, so are hyperparameters. And again, the data fidelity term, you can think of it as the least square term that we had before. So generally, to run t theta, we use something accelerated. Generally, this is the Anderson acceleration. And the original deep equilibrium framework is still a supervised end-to-end approach. The good thing is that usually it uses Jacobian-free backpropagation. So in essence, under suitable assumptions that are quite general, we don't need to compute any inverse of the Jacobian that might appear in the backpropagation formula when we derive this expression, and this makes it way easier for the training. A step further with this was proposed in a recent paper, so it's only a couple years old. And as I said, one limitation of deep equilibrium is that we still have a supervised fashion on like training, which means that in general, like in the approach I presented before, you need data and then you need the ground truth associated with that. Instead, in this paper that was proposed by the group of Kamilov, that works a lot in this field, they proposed to combine the ideas that comes from deep equilibrium with those that come from the approach called noise to noise. Even if you don't know at all what that is, what it means for us is that we can take different noisy realization of the same ground truth image. So we take the same UI, okay, and then we take different data starting from those, and then we train only using the data. So it's something called self-supervised, because you don't need the ground truth, but on the other hand, you do need different noisy versions of your data. And if you do this, they proved that if you take the samples, ED, you consider Gaussian noise on the data as we did before, and then you make an assumption on the masks. These are the masks that I introduced at the beginning of the talk that gives you the information about the subsampling of the measurements. And in their case, they consider an orthogonal operator because they were applying it in the context of magnetic resonance imaging. Then the Jacobian-free updates of the self-supervised loss, so this loss that I'm presenting here and that they introduced, are the same of those of the usual empirical risk that you would measure while doing training. Okay, so basically, if you train in a regime where you don't have the ground truth, you can do as well as training with paired data in a way, okay? And here, this W here is a diagonal matrix with weights that are related to the sampling of the angles. What we introduce, and this is pretty much the end of my talk, is that limiting A to be orthogonal leaves out problems like tomography. So we managed to extend this to the context of non-orthogonal, or in general non-unitary operators, by maintaining pretty much the same other assumption than we had. And we included in the training regime the projection to the positive ortant, which for tomography solution is always something good to have in addition to classic regularization. So again, part of the regularization lays in f theta. So this is for us a convolutional network. Think of it, for example, as a UNet. And then we also add a projection to the positive ortant. And now, if you consider a unitary operator, the price you pay is that the Jacobian-free updates are still of the self-supervised loss are still the same of the supervised loss, but the supervised loss also considers the operator A. So in particular, it kind of doesn't see the subsampling you are considering. On the other hand, by drawing uniformly at random your measurements, you have that the weighting matrix of the self-supervised loss is just a multiple of the identity. So it's you can factor it in as just a constant in front of your problem. And to conclude, I just show some numerical result to convince you that this kind of is an interesting direction to continue to pursue. So we are looking at sparse angle tomography with 16 angles. And so it's more angles than the approach before, but notice a thing, like an important thing is that in the training regime of pseudonet, we had kind of 10,000 images to do the training and then 500 for validation and testing. Here we are basically training on 32 2D slices, okay? So way less data. These come from a CBCT walnut data set. So these are parts of the walnut you saw at the beginning. And then we compare some zoom-ins of the ground truth with FBP, which you expect to do a bad job here, with total variation regularization, which produces a staircase effect, as also one who has worked with TV would expect. And then in the last column, this is what we can achieve with our method, and we compare it with another self-supervised regime introduced specifically from CT and for sparse CT kind of, I think, last year. So it's also very recent and combines, it's from the group of Altmaier. So it combines idea from regularization theory and again, noise to noise there. One thing that is important is that we have some links with the sparse to inverse protocol, in the sense that we kind of evaluate the loss in the sinogram domain as they do, but in our case, we know, thanks to the previous theorem, what to expect from the loss behavior, while in their case, they don't have any theoretical kind of result that can kind of guide their experimental numerics. And to convince you that the results in theory can be proved in practice, we see that the two lines we're interested in, so the green and the orange one, are actually pretty close, while the blue line is the supervised loss for unitary operators, so the one from the original paper. And of course, that loss does way better. So you're looking at the loss across epochs in terms of PSNR and SSIM. And of course, the, let's say, empirical risk does way better, but that's because they don't have A in there, right? So when we consider our loss, we are kind of missing the information on the subsampling regime. Okay, so because I don't want to overrun, but I know I left many details to be clarified, so I'm happy to take question now. What I hope I convinced you is that when you have scarce data and the inverse problem is severely imposed, classic regularization not always is able to help us all the way, but we can kind of still redeem some ideas, combine it with some other fields, and ultimately with deep learning. And altogether, we can get a solution that is not completely a black box, and we retain some understanding of what's going on, and continue to build on that to have a more interpretable solution while we extend on this. And with this, thank you for listening for almost 50 minutes to me. So I'm happy to answer any question you might have.
Thank you so much, Tatiana, for a very nice talk. So indeed, the floor is open for questions. So anyone that has a question, please unmute yourself.
Hi, I have a question.
Hi.
Thanks for the talk, Tatiana. Can you go back to the slide where you get only using six angles?
Yeah. So the first approach, yeah.
Right. So what do you use as a training set there?
So we basically have so it's a data set of ellipses with 10,000 images, where you have paired images of like ground truth images and subsample data. Okay, so you have the data corresponding to a sinogram with only 6 angles and the ground truth data. Okay.
And it's images of ellipses.
the images are these ellipses. So imagine you have a data set with many, many ellipses. You retain a portion to train, and then you have similar ones from a portion of this original data set, but not used for training, like any other, like the usual regime for doing learning that you set for validation, and another part that you set for testing. Okay, right. So there is no, I mean, if your question goes into the direction of can you train on this and then apply to something else, to other images, like that hasn't been used during training, we haven't done that. So, okay.
Yeah, that makes sense. I was also trying to just understand whether there's a discrepancy between what you use as training set and say like in terms of the number of angles you're using. Like let's say, are you using more angles for training and less angle on?
No, I mean, actually here, like this is a very important point because it's in some way a limitation of this type of approach, right? So because you have the geometry operator at every layer, right? Because you have this operator, if you try to train with a different geometry and with a different number of angles, it will not work. So if you train, for example, with more angle, or in the limited angle case with a different wedge, being it like smaller or wider, you would see precisely the artifacts coming from the geometry you used for learning if you apply to a different setting. So it's like really you are leveraging a lot the physics here. You cannot kind of train with different geometry protocols.
Thank you.
Thank you for the question.
Any other questions for Tatiana? I was wondering a little bit, Tatiana, for the first part, you sort of used hard wavelets, but mentioned that shearlets may be good for theoretical viewpoints. Do you think from the practical viewpoint, is it sufficient to use hard wavelets, or have you some practical advantage of shearlets?
So I think so shearlet, I mean, from an optimization point of view, using shearlet with iterative soft thresholding cannot really be done, because there you have, I mean, if you want to retain some convergence theory, and in the paper, even if I did not talk about it at all, you need something that is at least a bi-orthogonal wavelet to make it work with the convergence side of all of this. From the practical point of view, we are actually moving between you see, we have wavelets and wavelet transpose. So basically, we are mapping to and from the wavelet domain quite a lot. And wavelets are really, really fast, and shearlets are not. So if I just substitute these easily become a bottleneck. And while now our bottleneck is mostly the radon transform, like that's the most expensive piece, if we are plugging in shearlets, that is going to be more expensive. Okay, so even if here, like the image size is actually not that big, especially if we want to scale up and thinking how many parameters you have, it's going to be way slower. Okay, so now like we have an updated version from the original paper. It trains in like 2 or 3 hours, depending on some parameter settings. If you plug it in shearlets, I don't know, it raises quite a lot the times.
Thanks.
I have another quick question, if that's okay.
Yeah.
So it's related to how neural networks guess the missing singularities.
Yeah.
So what's the consensus there? I mean, what do people think the network is doing?
So you mean
I guess at some point you touched upon
here
the fact that it might be pushing the edges a little further.
Yeah, so as I was saying, it's like so the original ideas are contained in this paper by Gita and Ozan. So they have worked it out in details, and I think what they did is pretty much characterizing how the canonical relation of these operators works out. But at the end of the day, also their line was that this can happen, but you don't know when and how this can happen, right?
Okay.
So the best you can say is that when you apply the soft thresholding operator, and when the soft thresholding operator is acting on certain subbands of the wavelet, in our case, in their case, it was shearlets, and it's it's acting on these precise subbands that is describing a singularity, so it's kind of supported along a C2 curve, then you have hopes that it can bring some new edges at plus minus gamma, where gamma is exactly this parameter that you see here. What you cannot say is how do you see, I mean, when for sure this is gonna happen, okay?
Mm-hmm.
So in a way you have hope, but there is no way of expecting this. So if I go back to the images where you can see this, there are cases like this one where, you know, it was tricky, but it got in the reconstruction, so it worked well. And there are cases like this one where it probably was well in the measurements, but it's not there. So between the two, I would expect the one in the first line to be missed, as I see in this reconstruction, and the one here in the center to be recovered, but that didn't happen, right? So
wait, so yeah, in this picture, when you say 30 degrees, so you're which is the
plus
fan of
minus,
direction?
like imagine it's like plus minus 30 degrees. So you have an opening angle of 60
I see.
degrees total. So if you
Yeah.
think, I mean, it's very
I
small.
agree then, yeah.
You are missing 120 in this protocol scanning, but it's still like more than you have in breast tomosynthesis, where you have plus minus 20 degrees and then you have sparse angles. So it's still in a way generous compared to some actual devices available for commercial use.
Thank you.
Thank you.
Okay, if there are no more questions for Tatiana, let's thank the speaker again for a very nice talk. Thanks so much. It's very nice problem.